Assalamu alaikum. In the last class, we ended up at finding the theoretical value for the efficiency of a photovoltaic cell, which is made up of silicon. In today's class, we shall discuss in detail about the modeling of a PV cell, how it is electrically modeled, and what information is acquired once we model a PV source into its equivalent electrical element based model. So we discussed that whenever we expose the PN junction to the sunlight, then the photons which fall on the surface, they create the electron hole pairs near the PN junction, and consequently an electrical field is created in the depletion layer, which actually push the holes onto the p side and push the electrons into the n side. And if there is any load connected across the PN junction, something like this one, so let us say that we have this is n and this is p type. So when we have the photons coming from the sun, they strike this n type, and if we have anything connected here, some load is connected here, then the electrons move from the n terminal through this particular load to the p terminal, because the holes cannot move, and therefore only the electrons contribute in the current process. So when they reach the p side, on to this particular side, they recombine with the holes, thereby completing the whole circuit. However, this side is negative, this side is positive. So if we follow the conventional current, then the conventional current I actually flows from this positive side to the negative side. So this is a generic, circuit of generic representation of how the electrons and electron or the electric current is actually supplied to the load. Now, one more thing that we should understand here is that for like every electrical circuit that we have seen, the context of modeling ranges from the most simplest form of the equivalent circuit to the complex circuits, which represents the dynamics and the detailed modeling of the physical phenomena which happens in any given circuit. So we will start on the modeling of the PV panels, or of the cells, modeling of solar PV cell. So the simplest model, or which is known as an ideal model, consists of a current source and a PN junction which is represented by a diode. This constitutes the simplest equivalent circuit of a PV cell. This ideal current source it is responsible to deliver the current in proportion to the amount of photons or amount of the sunlight which is available to this photovoltaic cell. And of course, the theory that we have studied so far, that those photons only contribute to the production of electricity which have their EV, or the electron volt, or the band gap energy more than 1.12 for the silicon. So there are 2 points of interest for any given solar cell, which is, the first thing is, what if we short circuit these two terminals? So let us say that if I short circuit this one, then we have the current flowing through this branch. It is the short circuit current, and consequently when it short circuits these two terminals, then this current ID becomes equal to 0, and all the DC current which is generated by this sunlight, it actually flows through the load. So this is one thing. So the other important thing which is of our interest is the condition when the output terminals are left open. So if we leave this open, then the voltage that is produced here, we call it VOC, because it represents an open circuit condition. In an open circuit condition, we have no current flowing at the output, so I is equal to 0. So based on these two important parameters, which are the open circuit voltage and the short circuit current, we can write the equation which expresses the relation between the voltage and the current by applying the KCL on this particular node. So let me redraw this circuit again. Now we have a current source. Here we have the diode, and here let us say we have some resistance which flows here. So the current which is flowing here, the current which flows here, I, if I apply the KCL here, then this I is equal to ISC minus ID, and ID is this current which flows through this element diode. So the Shockley diode equation says that for any given diode, the current ID is equal to I naught e raised to the power q Vd by kt minus 1, and this equation is known as the Shockley diode equation. We will substitute this particular equation into this equation for into this KCL, which gives us the output current flowing through a given PV cell. So this I becomes equal to, using this particular equation, this I becomes equal to ISC minus I naught e raised to the power q Vd over kt minus 1. So what we are seeing here is that this ISC, it is actually a constant DC current, and this one is a current which is represented by the Shockley diode equation, and it is the forward current through a diode when it is forward biased. So essentially what we need to do is to subtract this diode current from this constant DC current. If we subtract these two together, if we subtract this diode from this from this ideal current source, then we get this type of a characteristic curve. And in this characteristic curve, you can see that this particular point has 0 voltage, and consequently we call it the ISC, or the short circuit current, while this point where we do not have any current is known as the VOC, or it is also known as the open circuit voltage of any given PV cell. Now one important point here is that the characteristics of the PV cell is not linear. If we see this particular characteristic curve and we try to find out what is the value of this VOC, then this VOC value can be achieved by putting this I equal to 0, because the VOC will only happen if we do not connect any load resistance RL here. So for instance, if the load is removed such that we are having nothing connected across the PV cell, for instance, let me draw this one here. This is ISC, and here we have this diode, and I make this one open circuit, so this I become equal to 0. Now if I becomes equal to 0, then this particular equation, let us say that this is equation number A, then this equation number A becomes equal to VOC, that is equal to KT over Q log of ISC over I naught plus 1. And if we plug this value of T equals to 25 degrees centigrade, the equation, this particular equation at 25 degrees centigrade, this VOC becomes equal to 0.0257 log of ISC over I naught plus 1. Also, if we put the value of T equals to 25 degrees centigrade, this equation number A becomes equal to I is equal to ISC minus I naught e to the power minus 1, right? This particular equation as well as the equation for the VOC, we can see that the amount of short circuit current, this particular current value ISC, it is directly proportional to the amount of solar insolation, which means that if we have a set of irradiance values, we can plot a set of the PV curves for any given PV cell. So we can say that if we have the maximum sun available, let us call it 1 sun, we have this much amount of ISC available, and if we have lesser amount of sunlight available, then we have this type of PV curve, and so on and so forth. So with the change in the irradiance or the change in the falling light, the major impact is seen on the value of the current, which is the short circuit current, while we can see that there is a very limited change in the value of the open circuit voltage. Now in this particular equation, this VOC here, this ISC is dependent on the solar cell area, how much area is exposed to the sunlight. This I naught is usually known for a given solar cell. So now it is quite visible that we have very substantial change in the value of the ISC. So this is, let us say, this is ISC1, this is ISC2, and this is ISC3, and you can see here that ISC1 is greater than this ISC2 and it is greater than this ISC3, and both of them also represent that the amount of sunlight received to the photovoltaic cell when it produced this ISC1 is greater than the amount of sunlight received at 0.75 and this ISC3 value. Now if we notice here that this is the VOC value, and we have seen here that this VOC value has not changed much. So let us perform a simple numerical to understand how and why this is actually happening. So we consider that we have 100 centimeter square PV cell that has an I naught equals to 10 raised to the power minus 12 ampere per centimeter square. Now it is stated that this particular cell at the full sun, at sun equal to 1, at sun value equal to 1, it gives an ISC that is equal to 40 milliampere per centimeter square, and that is at the 25 degrees centigrade junction temperature or the cell temperature, right? So this is not the ambient temperature, it is the temperature of the junction. Now if I plug in these values in this equation for this VOC, then this VOC becomes equal to 0.0257 log of this ISC, and this ISC we need to calculate because it is 40 milliampere per centimeter square, and because the size of a PV cell, for example, if this is the PV cell, so the size here is 100 centimeter square. So this becomes equal to 4 divided by I naught, which is 10 raised to the power minus 10 plus 1. So this VOC value is equal to 0.627 volt. So now there are two important things here. See, if we have a solar cell of a size 100 centimeter square, even this small size, it is capable of producing 0.627 volt across itself while having a substantial amount of ISC, which is equal to 4. Also this I naught is a function of the ampere per centimeter square, and we have to calculate it according to the area given, which is 100 centimeter square, and consequently we are having this 10 raised to the power minus 10 in here. So this is 0.627 at even a very low value of the cell voltage. It is able to provide a short circuit current equal to 4 ampere. Now let us say that we have the sun, the irradiance is practically half. So if the sun is half, and we have earlier seen that this, I said that this ISC is proportional to the amount of irradiance G, where G is the irradiance here. So at point 0.5 sun, the straightaway effect is on this ISC value. So this ISC becomes equal to this 2 ampere. So now if I plug this 2 ampere back to this particular equation which represents this VOC, then this VOC equals to 0.0257 log 2 into 10 to the power minus 10 plus 1, and this gives me a value equal to 0.610 volt. Now if you see here that with the change in the irradiance, the ISC has practically become halved, while there is a very little change in the open circuit value. Now this particular model of the PV cell, it is very simple. We have only 2 elements in it. It has an easy understanding, but it is not able to plot or to model the complete characteristics of a practical PV cell. Like this is quite uncommon in most of the cases, because whenever we create an ideal model, mostly that ideal model is able to plot the characteristics of a device, and this is what we can get here. But we have another problem with this particular model, and that is that this ideal model, although it is simple, it is not able to reflect or model the PV cell under shading conditions, right? So let us see how and why it is not possible. Now, for example, we have 2 PV cells which are connected in series. So let me have, this is cell number 1, and this we have another PV cell. This is cell number 2. They are connected in series, and we have a resistance which is connected across the series connection of these 2 cells. So now if you see here that we have these 2 cells in series, and therefore the current through these must be the same. Let us say we have this particular cell in shading condition, which means that this cell is not producing any current, so this I equal to 0, but we do have the sunlight available on this particular solar cell, so it will be operating at this ISC value or the amount of current which is produced at a given irradiance condition. So now the simplified or the most ideal equivalent circuit that we have studied here, it cannot be used, because its diode will also be reverse biased, and consequently there shall be no current flowing through the load. So the load current I will be equal to 0 because of the shading of this PV cell. So although we have seen that it is that this current ISC is proportional to the value of the falling irradiance G, this is not a very senseful condition, that we are saying that even if one cell is shaded in a series connection, then the load current becomes equal to 0. So this requires to have an additional component in the system model where we can actually deal with the shading problem in details. One such particular model is known as the shunt model. Now the shunt model has a resistance Rp in shunt with the, or in parallel with the existing ideal 1D model, right? So with this thing in place, the new circuit, or which is known as the shunt circuit, has diode here, and here we have the resistance. Let us call this one as Rp. This is ID, and this is the ISC, right? Now, with this thing in place, this Rp is in place, there is some current which flows through this shunt path as well, and therefore the KCL which is applied here, it tells us that the current I is equal to this ISC minus ID minus IP, and this IP is equal to V over Rp, and consequently this I is equal to ISC minus ID minus V over Rp. So let us first of all see that what is the impact of adding this resistance on the characteristic curve of a PV cell. So there is no resistance, which means that this Rp is equal to infinity and this Rs is equal to 0. So no current flows through this shunt branch and there is no losses in the system. So, but if we make this Rp not equal to 0, or we include this just like in a shunt model, then we have this type of a slope, and this represents this Rp is not equal to infinity, and the change in this current I between this point and this particular point, let me call this delta I, that is equal to V over Rp, because this is the change in the output current value because of the presence of this resistance Rp. So having said that, the slope here, this particular slope of this line is equal to, this slope is equal to 1 over Rp. So what we are actually witnessing here is very interesting, that for any given condition, the parallel resistance Rp which we have modeled, actually it reduces the load current, and this reduction is by a factor of V over Rp that we have shown here, this particular point. So this means that this Rp is something which is a form of a losses, right? This is a losses, and this losses occur because of the electron hole recombination which happens before they reach the output terminals. So for a given PV cell, if we want to reduce, if we want to have the shunt losses less than 1%, then this Rp should be greater than 1000 VOC over the ISC, where this VOC over ISC is the value of the output voltage and the generated current ISC. So for example, if we talk about a typical PV cell, we have this ISC something equals to 7 ampere, and VOC, as we have seen, is in a close vicinity of 0.6 volt. This calls for an Rp should be greater than the 9 ohm. Now this particular PV model can be used to see the impact of this particular two cells connected in series. But before we move on to the impact of shading on a PV cell, let us introduce the losses which encountered because of the contact resistance of the metal, which collects the charges. So on any given PV cell, we have these type of two conductors which actually collect the charges which are placed over a PV cell. Their resistance also encountered for a loss in the system. So let us first of all model this particular loss in a system before we create a comprehensive single one diode model including the impact of this parallel resistance and the series resistance. So this particular model is known in the literature as a series PV model. One diode, 1D series model. This series model contains a current source which is the ISC, a diode where the current flowing is this ID, and then a resistance RS. Here we have this is equal to VD. So this RS represent two things. One is the contact resistance. It can also be the resistance of the semiconductor material itself. So now if we apply this particular thing, then the current I, which is flowing here, this I is equal to this ISC minus ID, and this we have already seen, that is equal to ISC minus I naught e to the power q Vd over kT minus 1. And now we need to include the drop across this RS, because the current which enters here is essentially the same which we are having available at this output I. So what is the Vd here is of importance. So this Vd, which is the voltage across this diode, that is equal to, sorry, this is V naught, sorry, this is equal to V only. So this particular Vd is equal to V plus I into Rs, and this I is actually substituted in here. And if we substitute this particular value in here, then we have I equals to ISC minus I naught exponential of Q into V plus I into Rs divided by KT minus 1. Now the impact of this particular resistance Rs is not on the current, because this Rs is actually decreasing the amount of voltage which is available at the output, right? So if we draw the characteristic curve here, if we draw this characteristic curve of a PV cell, so let us say this is for a cell where this Rs is equal to 0, then if the Rs is not equal to 0, then the effect is seen on this particular side, right? And this is the Rs not equal to 0, and the amount of the major impact is seen here, which is said to be the delta V, which is equal to I into the amount of resistance Rs here. If we want to restrict this series losses to a value which is less than 1%, then this Rs should be less than 0.01 VOC divided by the ISC. And for the same cell that we have studied earlier, for this particular case, ISC equal to 7 ampere and the VOC equal to 0.6 volt, which is a typical solar cell, the amount of Rs should be less than the 0.0009 ohm in order to achieve a VOC equals to 0.6 volt and the ISC equals to 7 ampere. Now this series loss and the shunt loss, both of them are reported in the literature as a series model as well as a shunt model. Now remember that the concept of modeling a diode in its detail ranges and revolves around different factors. So for example, a PV module or a PV plant, it is not wise to include all the resistances in the system. Most of the times, researchers have argued on various factors which decide for the choice of accurate model for a given PV module. For this reason, if we include the Rs and Rp, both of them are actually introducing one extra amount of information for a given PV cell. And usually it is stated that the PV model, which is a good compromise between accuracy and simplicity, is a model which is known as a complete one diode model. One diode model of a practical PV cell, and that contains the current source, this PN junction diode, this resistance Rp, and this resistance Rs. And this particular model is known as a one diode model because we have only shown one diode to represent the PN junction. Some more detailed information can be seen in the literature review, where you can see that there are two diode model as well as a three diode model. So with this model in mind, we have this is ISC, this is ID, this is IP. Then we have a drop here as well across this resistance Rs, and consequently we have at the end we have this VPB and this IPB available here. Now, if we solve for this particular circuit, then the model of the PV cell and its corresponding equations at the output are altered such that we have this I, that is equal to ISC minus I naught exponential of Q into V plus IRS divided by KT minus 1 minus V plus IRS over RP, right? So this is the current which is flowing through this parallel resistance. So this part is the shunt part. This I naught represents the ID, and this is the actual current which is generated from the sunlight, and we usually call it a photocurrent, where this I is the output current here. Now this particular equation contains some information which is of our interest, and we will try to see how we can use this information to assess the performance of a given PV cell at T equals to 25 degrees centigrade temperature, which is again the cell temperature. This I becomes equal to the value of ISC minus I naught e raised to the power 38.9 into V plus IRS minus 1 minus 1 over RP into V plus IRS. Now this equation contains a lot of variables which are not given by any manufacturer, because usually when we go in the market, we buy the PV photovoltaic panels, and a small amount of information or what you can say a very brief set of information is given in the form of the data sheet or in the form of the specification which is written on the back side of the PV module. It do not provide you anything about this ISC. This ISC is unknown. It do not provide you anything about this I naught, right? Furthermore, because we have the diode modeled in the datasheet, do not provide you the ideality factor of the diode. It also do not provide any information about the parallel resistance as well as the series resistance. So for a one diode model, for a 1D model of any practical PV cell, there are 5 unknown parameters which have to be calculated based on the falling irradiance and temperature values. And therefore, this equation is not at all a trivial equation, and some iterative method is required to solve for this ISC, I naught and this RP value. In order to solve for this particular equation, we have worked on this particular thing that is available in my research paper, a grade point average assessment of analytical and numerical methods for parameter extraction of a practical PV device. And this paper is published in Renewable and Sustainable Energy Reviews. Now, this work was done by graduate student, and here we presented and analyzed different methods which are used to identify these 5 missing parameters for a single diode cell, although the paper contains information about a 2 diode PV model as well, but that is well beyond the scope of this particular course. So we will stick with the with the basic approach, as I have said that we have to have these 5 unknown parameters here. The first one is this one, then we have this one, again we have this alpha is unknown, this RP is unknown, and this RS is unknown. So there should be some method to identify these values based on the environmental conditions, and a framework is actually provided based on the Newton-Raphson method. So the flow chart is as follows, that we start the system, and then we define the constraints for constraints and the PV parameters. Whatever parameters are given in a given PV data sheet, we specify here. Thereafter, we define the objective function, and then based on this objective function, we calculate the ISC, ID, and the reverse saturation current I naught. Thereafter, we evaluate the value of I based on the Newton-Raphson method, or any other numerical analysis method can be used, and we calculate also the absolute error here. And this error has to be contained to some value, so there is a conditional statement block here. So if this absolute error is less than the tolerance, or whatever the value is defined, because you need to terminate the program after the error is contained to a certain value. So this is defined by this tolerance. If it is not within this particular tolerance level, then we go through this optimization algorithm block, and we again calculate the value of this IPH, and this loop continues until we finish up with a value of the IPV which is within the range of the absolute error. Now this optimization algorithm, we worked on almost, I think, 8 algorithms in this particular paper. I will share the link of this paper as well in my video. This optimization algorithm, once you create this optimization algorithm, it will always go through that. For example, you can use the PSO, particle sum optimization. We can also have the genetic algorithm. We can have the Nelder-Mead simplex method, and other various algorithms. So whatever algorithm you have coded, you can plug it into this particular block to calculate the value of this ISC. The main point is that once we have this algorithm, then based on this Newton-Raphson method, you have to bring this absolute error within the range of the tolerance value. And if it gives you the value which is less than this tolerance value, then it will output the PV parameters. And these PV parameters are 5 for one diode model, they are 7 for 2 diode model, and they are 9 for a 3 diode model. 5 unknown parameters are to be the output of this particular program for this PV cell, and thereafter we end the particular program here. We can see that the individual cell here is able to produce some acceptable amount of current value, but their VOC value is quite low, which we have seen is something around 8.6 or 0.7 volt per cell. Therefore, several cells are connected in series and parallel to create a module and then to the array. And this we will discuss in our next class. So till then, take care. Allah Hafiz.